welcome back. We left off last week discussing an object which was meant to be the classical version of a fermion. And this object is called a Grassmann number. So if you recall from last week, we defined the Grassmann numbers to be generated by a set of vectors in some vector space V, you choose some set of basis vectors theta 1 through theta n of some vector space V. You adjoin the symbol 1 and you impose some relations. Namely, that these generators anti-commute with each other for all j and k. So this is the Grassmann numbers. There's the additional relation that 1 times theta is theta. So 1 doesn't anti-commute with everything else. And then once you do this, you get a new vector space, which is 2 to the n dimensional. So GNV is a 2 to the n dimensional vector space. And we have a basis for this vector space. We have something called the monomial basis for this vector space, which comprises all these basis vectors in order. It's a pretty simple argument that these are the only vectors that can appear in a basis, that if you had a bigger basis, that one of these monomials would have to be 0. So there's 2 to the n of these. And therefore, if you have a basis, an arbitrary element of the an arbitrary Grassmann number or Grassmann variable is then a linear combination of those things. So that's approximately where we were last week. Yeah, and these things are numbers. So that's where we were last week. We have this vector space that we've defined. And so far there's no reference to physics whatsoever. You're not meant to think of these things as classical fermions or anything like that. You're just meant to think of these things as what they are, which is as elements of a vector space. And this vector space is a useful thing to define for later on when we do we want to define something that could be called a path integral for fermions. But for now, it's just some vector space, some abstract vector space. In the next, throughout this lecture, we're going to try and build a kind of calculus for this vector space, something that looks like differential calculus and integral calculus. But you must be aware that we're just going to be talking about linear maps on this vector space. Although we're going to be using lots of calculus notation, you're not meant to think of these things as being defined by limits or anything like that. This is just a suggestive notation. Before we can do calculus, we need functions. So we think of these you're meant to think of these things as anti-commuting numbers or variables. Like x, like the independent variable x when you have some function of x. And if you're meant to think of it like that, then you're entitled to ask, well, what's the area under a curve? Well, there's no answer to this question. There's no canonical answer. You have to invent an answer, one that makes sense and is useful for you later on. And that's what we're going to do. We're going to invent a whole bunch of operations on these variables, theta, that have properties we would demand from normal functions and normal numbers and normal integrals and normal derivatives. But it's all by analogy. This is important to stress this. Yep, question?
To the basis.
Yes.
This looks like a PVD base, and so it might be the universal enveloping of the Lie algebra.
It looks like a what basis, sorry?
Poincaré-Birkhoff.
It looks like a Poincaré-Birkhoff-Witt basis. Yeah, I mean, so these are universal constructions. They occur throughout mathematics, that you get some objects, you freely generate another object from those objects, and then you impose relations. And this is exactly what you do with the Poincaré-Birkhoff-Witt theorem context. But at the moment, this is just a vector space.
Okay, so it's not, it corresponds to the Lie algebra, it's just the same.
At the moment, it doesn't correspond to any Lie algebra. We don't have an underlying Lie algebra structure on this vector space V. So V is just a vector space. It has no other structure. Whereas with a Lie algebra, you already have a kind of a bracket operation that you impose on the vector space. We have not yet imposed any such structure, so it's actually got less structure than a Lie algebra. But absolutely, this free generation of objects is something that you do in Lie algebras as well. And, well, not just Lie algebras, it turns out there are deeper category theory reasons for why these things appear everywhere in maths. To do with far out mysteries called left adjoints. But we will try and avoid category theory in this course. Right, we're going to think of these guys as anti-commuting numbers. and when you have or a variable, and when you have a variable, you might want to take a function of that variable. So the first question we're going to focus on and I'm going to put in quote marks every time I say something that may not have a unique answer. That every time we're looking for a definition, I'm going to put quote marks around it. So we're going to look for how to define functions of Grassmann variables. It's a question. How do we define it? There's multiple ways you could think of defining these things. Like here's a in quote marks wrong definition. Definitions can't be wrong if they're consistent. They're definitions, right? But this is the one that doesn't capture what we want. So let f be some infinitely differentiable function of the real numbers, and just simply one thing you could do is just adjoin this symbol f of theta and make sure it anti-commutes with everything. So there you get a new anti-commuting object for every function, every infinitely differentiable function of the real numbers. So that quickly leads to an uncountable number of objects, f of theta j. This is clearly not capturing what we want. This is not how we think of functions, right? And there's multiple things you could do here. This is not the only way to define a function of a variable. But there's more structure that you want something that looks like a function to have. One thing would be you'd have linear functions, right? You could start with linear functions and say, well, what could that be? So there are things that are a little clearer, right? A linear function on a vector space, we know what that is. It's a map from a vector space to the vector space. So functions should at least be maps. Still putting quotes around it here because we're just looking for a definition, and once we settle on a definition, we'll stick with it, and then we'll hope that it's useful at the end. But, warning, there are other definitions you could think of making. So I'll start with linear functions. Linear functions, what are they? Well, they should take a Grassmann variable and give us another Grassmann variable. So this is a pretty natural thing to want to impose. They should be linear maps. Linear functions ought to be linear maps from the Grassmann numbers to the Grassmann numbers. I.e. f is somehow an element of the 2 to the n by 2 to the n matrices. So this is indeed the way we're going to take, the route we're going to take to defining functions of Grassmann numbers. They should be maps. And the only difficulty is extending this definition to nonlinear functions. What on earth is a nonlinear function going to look like? Well, we're going to do what we do when we ask the same questions of matrices. So linear functions, I think you'd have to be pretty, well, particularly bloody-minded to want a definition that isn't like the one I've written down there for linear functions. But nonlinear functions, again, you're sort of in this setting where you've got to, what's the right definition? You could cast around trying out different things. But to do this, I just want to point out that there's a setting where we can define nonlinear functions of things, and we've done it successfully, and it's been useful, and that is in terms of matrices. So we're going to work by analogy with the matrices. Again, this word analogy, we're not really saying that these are functions, or we're defining by analogy. So there's this thing you've met somewhere in your career called the functional calculus. You take some operator and you define some function of that operator by diagonalizing the matrix and then applying the function to the eigenvalues. So as long as M is diagonable, then f of M is just the functions of the eigenvalues rotated by the matrix which diagonalizes M. That's how we define functions for matrices. Diagonalize, then you know how to define a function for a diagonal matrix. It's a commutative algebra. And then you just rotate back again. And that's the definition here. So we're going to work by analogy with this. And I guess the standard way people who do this in textbooks is they say, let's just let's build a Taylor series and then define our functions by Taylor series. There's another way to do it, which is to first represent our Grassmann numbers as matrices, then just use the functional calculus to define functions. They're the same. Essentially the same. One way you could think of defining functions of Grassmann numbers. Okay, it's slightly awkward because now we're working with a representation of an object rather than the object itself. In the end, we're going to just make a definition that works for the Grassmann numbers without reference to a representation. But for now, this is a good way to start to discover how to define these nonlinear functions. Okay, so then we've created another problem, which is how to represent our Grassmann numbers as actual matrices rather than as elements of a vector space. I mean, they have this product rule, right? So we want to respect that with a matrix product rule. So we want that when we have a Grassmann number and we find a representation of it, so remember, a representation is just a map from your space to some concrete matrices. If you want, what does a representation have to obey? Well, it has to obey the defining relations, namely that. with a little bit of work, you can extend these relations to work for all the Grassmann numbers and this representation to be a proper representation of this object. I'll give you one example of a concrete representation of these Grassmann numbers that's faithful enough that we can define things in terms of the representation, or at least guess what the right definition is. Okay, you've already seen this representation before. I like it very much. I guess I'll call this the... I don't have a name for it, but... I just want to give you an example of a concrete representation of these objects. So you have something in mind. So we start with a Hilbert space. H is 2 to the, what are we going to need? I guess 2 to the n. And we have these Pauli operators. We're only going to need 2 Pauli operators. Namely, sigma plus and sigma z, and you can check that sigma plus anti-commutes with sigma z. Yes. And you can also check that sigma plus squared is 0. So these are very interesting properties for our representation. What do I mean by this? Thank you. I mean that c to the power of 2 to the power of n. Sorry, or that the dimension of the Hilbert space is 2 to the n. All right, and then we're going to define a bunch of operators. So pi of theta 1 is sigma plus 1 tensor the identity on 2 so you've seen this before, you know what's going to come. I think that works. Yes. All right, so you build these n matrices, sigma 1 plus tensor with identities to the right, and if you're somewhere in the middle, then you tensor with sigma z's to the left. And you can check, and it's not hard to check, from these 2 identities here, that this is indeed a representation of the Grassmann numbers. We actually get every single Grassmann number that we want here. And now we can just define But, we can attempt a definition now of what a function is of these guys. So we're going to start with the single variable case. G1. So this is the vector space, which is the single Grassmann variable, single Grassmann number. So this is just the space of A plus B theta such that A and B are complex numbers. So I should say this is what you might call the single variable case of defining a function of Grassmann number. And well, what should it obey? How should this definition work? Well, it should behave nicely, or should be the same as the functional calculus on the representation that we have there. Let's say consistent or compatible with turns out to be rather easy. Because all these matrices are in Jordan normal form already. There's a perfectly straightforward way to do that, and that is you first write out the Taylor series for the function f. And then you just substitute in place of x pi of theta or whatever you have. And there's a very nice property of this definition, and that is that it terminates after two terms. So after two terms, everything else vanishes because theta squared is 0. This definition is not without its peculiarities. So So something that you might consider to be a bad feature of this definition is that many normal functions that are completely different end up being exactly the same things when applied to Grassmann numbers. I'll give you an example in a second. Two examples. So is this bad or good? It depends, right? It depends on what you do with this stuff later. Let's do a kind of interesting example. Let's take the function sine of x. So what is f of theta? Well, we use the Taylor series for sine of x, and the Taylor series is x minus x cubed on 3 factorial, blah, 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 blah. And then we substitute in place of x theta. And what we find is you get theta minus theta cubed, and that's 0. So sine of x is, sine of theta is just theta. All right, fine, that's a consequence of the definition we've written down. Then we could choose other functions. And we have all kinds of strange things that happen. We could take just the function, well, x plus x cubed. Well, again, f of theta is theta. So with this particular definition of a function of a Grassmann number, we have the good feature that we can concretely calculate what this function ought to be, and the, perhaps in your view, bad feature that many very different functions, such as sine of x and x plus x cubed, are exactly the same functions when applied to Grassmann numbers. So it turns out this is a useful definition. It's one that will turn out to be quite handy when we define path integrals, but be aware it has some very strange features. And this is the first really strange feature, that when you define these functions, many very different functions in the standard continuous functions turn out to be exactly the same maps when applied to Grassmann numbers. And now, that was just the single variable case. Let's do the many variable case. So if f is some continuous function from R cross n to R, so you have some function that takes n variables and gives you a number. And you might wonder, how would I define this for our Grassmann numbers? Well, again, we just use the Taylor series, but we use the many variable Taylor series to define this object. I'll just write out the first couple of terms. There are higher order terms when you have many variables. You might be forgiven for thinking, oh, then all functions of Grassmann numbers are just linear, but that's not true. When we come to the many variable case, we can get many more interesting examples. So I'll give you one example. So And this is the only example we actually care about in all this, in the entire course. There's no other example that we care about. It's only this one. So I call it, why bother with the 1? It's just the example. And our example is a Gaussian. Well, sort of a Gaussian. Wait, I've already done. I'll put x, y here. So e to the minus xy, minus lambda xy, is a perfectly well-defined continuous differentiable function. And we might ask, what is the corresponding Grassmann function? And we get a kind of interesting answer. The first rule is, I'm going to sort of cheat. You just stick in thetas where the x's and y's are. And this must be understood by a Taylor series. We need to do a Taylor series before we've evaluated this. So let's do the Taylor series for the exponential. So this is 1 minus lambda xy plus lambda squared x squared y squared, and so on. And actually, we get something that looks a little different. It still has a linear term, so to speak, but because it's now many variables, we can get higher order terms. Actually, I lied. We'll do 2 functions. This is still example 1. I'll continue with example 1. Okay, that was easy, right? Because the Taylor series just vanishes for all the higher order terms. Let's do example 2. I'm not even going to write the original function anymore. Just look at this function here. What is this equal to? Well, again, you do the Taylor series, right? This is the same thing. Always you define these functions by their Taylor series. 1 minus lambda 1 theta 1. Every higher order term vanishes. All the higher order terms vanish. And then when we expand this out, we don't just get 2 terms. We don't just get a constant term and a linear term. We get 4 terms. 1 minus lambda 1 theta 1 minus lambda 2 theta 2. But there is a higher order term. So nonlinear functions reveal themselves. They become... the nonlinear features become more evident when you have multiple variables. But with a single variable, all nonlinear functions collapse to linear functions. It's only when you have multiple variables that they start to look different when you're defining functions for Grassmann numbers. All right, that was functions. Let's do complex Grassmann numbers. Again, the quote marks appear. This means I'm going to give you a definition by analogy rather than, proving that this is the correct way to do things. So we're going to define them by analogy with the real and imaginary parts. So we're going to define a complex Grassmann number simply to be the linear combination of two Grassmann numbers, where we have, and we think of theta 1 and theta 2 as like the real and imaginary parts. And we're also going to invent another symbol called theta star, where theta star is that other Grassmann number here. So these are both elements of G2. We're going to call them complex Grassmann numbers when we have theta 1 and theta 2. There is a deal of arbitrariness in how we do this. And we're also going to define an operation star, which takes the complex conjugate of a complex Gaussian. And I'm immediately going to extend the whole definition to the many variable case. So just as you can think of complex numbers as like the two copies of the real numbers, you can think of complex Grassmanns as two copies of Grassmann numbers. All right then, enough with functions. Let's do some calculus. We're going to define something that we could call a derivative of a Grassmann number or a Grassmann variable. Again, there's multiple definitions you could dream up, and you have to choose the definition that does the right job for you. So that's what we're going to do here. We've got to choose those features of what a derivative is that are most useful for us. So people have experimented with this, and they have a definition of something that you could call a derivative. Now, our definition is that So the derivative is a derivation, which is a kind of linear map from the Grassmann numbers to itself. So what the derivative should be, it should be something that takes a Grassmann variable, a Grassmann number, and hands you back maybe a different Grassmann number or Grassmann variable. So it has to be a map between these two this space. But this map can't be just any map. We're going to have to give it some conditions that we'd like it to obey by analogy with the standard derivative. So what we want this derivation to obey, this derivative to obey, is we want it to behave like a derivative. So we want it to obey a kind of chain rule and a kind of product rule. That's like our most optimistic hopes would be to find a definition where this thing does exactly what the classical derivative does, but we must be prepared that what we invent might behave slightly differently in certain cases. So actually I'll just change the notation slightly. I'll just turn it into a partial derivative sign. There's some reasons why a D is not quite the best choice. So we want that, well, you know, what's rule number one? Well, we would want that if you do the partial derivative with respect to variable theta j of some other independent variable, you better get 0 and 1 if they're the same. So I think that's a pretty reasonable condition to demand of any derivative. If you differentiate the variable itself, you better get 1. Another one which is kind of useful to have is something analogous to the product rule. Now here we already have to be a bit careful, or the Leibniz property of this derivative. We always have to be a bit careful when we have anti-commuting objects. So the first thing you might try actually fails. So what's the first thing you might try? Well, you might say that the derivative with respect to theta j of some product of thetas, well, you just go through and find the theta in here that's the theta j, you get rid of it, you put in the symbol 1, and you're done, right? That should be a reasonable definition. But the problem is you run into issues with minus signs. So I'll give you the next best thing for a definition. Okay, it turns out this is the correct definition for how the partial derivative acts on products. This is a very complicated looking expression, but it just does it does what I just said, which is it goes through, yeah, question?
Why is there J1 and J2 and so on? There's just
Oh gosh, sorry, why is there a J1 and so on? There's just a J. And I got confused with subscripts, so that's a comma. So that's J comma K1, J comma K2, all the way up to J comma KP. All right, so it turns out this definition basically does what I said up to a minus sign. So it goes through the product, finds if the variable theta j is there, gets rid of it, replaces it with 1, which is fine, but it gives you a minus sign if you've had to pass, if it's if it's in an odd place in the sequence in this monomial. All right, life is good here. It looks just like the normal derivative. Slightly different here. I could justify this definition here as follows. So you could think of this definition that I've just written up there as first bring theta j to the front and then differentiate. So in terms of our example, d theta 2, d theta 1, d theta 2, theta 1, theta 2 should be the same as, well, it's got to be a linear operator, so it's going to be the same as minus d theta 2, theta 2, theta 1. And then, well, it's at the front, so we differentiate as normal. What I didn't say, but I hope is clear, is you extend the definition by linearity to apply to any element of any Grassmann number. So it's a good little exercise to prove that this definition here obeys the product and chain rules, as you would hope for a derivative. So this is a reasonable counterpart for a derivative operation, derivation. It's basically the same, except sometimes you get minus signs. And the justification for the minus signs is that you should always bring the variable you're differentiating with respect to the front, and that might give you a minus sign before you differentiate. All right, integrals. Again, we're going to define things by analogy. Integrals, what are they? They must be some kind of function that takes some Grassmann numbers and gives you some numbers. So these are definite integrals. So if you think of the integral operation on a function, what does it do? It eats a function and gives you a number, the definite integral, from minus infinity to infinity. So this should be a linear map. And it should take a Grassmann number and give you a proper number at the end, right? Because that's what the integral does. It takes a function and gives you a number. So this should take a Grassmann, it takes some linear combination of variables and gives you a number. So whatever an integral should be, it should be a linear map from the Grassmann variables to just numbers. And you can, well, again, you have this problem, what's the right definition? Well, there is no right definition. You can't prove that one definition is right and one is wrong. All you can do is choose properties that you like this definition to obey, and then check that that's a useful thing. And see if that singles out a particular definition. And indeed, there is one definition which is better than the rest. So whatever our definition is, we want it to obey a kind of shift invariance. So that if you send theta to theta plus eta, well, this is just some other Grassmann variable. Then when you do that shift, you should get the same answer. That's a property that you might like about the integral. Now remember, we're obsessed with Gaussians in this course. And this shift invariance is crucial to proving stuff about Gaussians, like how to do an integral of a Gaussian. You always shift your variables of integration. So it's something that we would hope to be able to keep in any general definition of an integral for Grassmann numbers. And if we impose this condition, it turns out there's only one definition that is consistent. Only one definition which is consistent with this. And that is that integral, I'm going to drop the limits because they don't make any sense anyway for Grassmann numbers, that the integral of a plus b theta is theta, is b. It's actually the only definition which is consistent with shift invariance. I mean, the first term's got to vanish, right? For any definite integral, constants are going to go. So we're left with that as our other option there. So this leads to the definitely the following bogulating identity. Integrals are the same as derivatives for Grassmann numbers, at least of single variables. It's actually true in the many variable case as well. So the general definition of a many variable integral for a Grassmann number, well, once you identify it as the derivative in the single variable case, then you can just identify it as the derivative in the multivariable case, and you're done. So if you take some arbitrary element of the Grassmann numbers, then the only option which is consistent with shift invariance is to just differentiate with respect to all the variables, one after the other. And that leads you to the definition that it just picks off the highest term in the Taylor series. And that's it. That's the definition. As weird as it is, we're stuck with it. It's the one that works and does what we want later on. This definition also behaves correctly under changes of variables. So that's and also a key property you'd want to maintain for any definition. Okay, let's do one super important example. Namely, a complex Gaussian. Let's do an integral of a complex Gaussian. So what is this going to be equal to? Well, remember theta star and theta are just independent Grassmann variables. So step one is to first evaluate this function of Grassmann variables in terms of Grassmann variables, and you just do the Taylor series and truncate at first order. The next thing is to realize that, of course, that theta and theta star are just independent Grassmann variables. So they anti-commute with each other. And then the next thing after that is to realize that the integral is just defined in terms of the derivative. And the final thing is to be a little bit careful about the minus sign. So we're differentiating first with respect to theta, but the theta is in the wrong place. We have to bring it forward or just use the other definition of the derivative. So we get a plus sign. So the answer after all of that is just lambda. So the last thing we're going to do today is evaluate the many variable Gaussian integral for Grassmann numbers. I mean, we could talk about this a lot. There's a really fascinating part of physics and maths called supermathematics, where you combine Grassmann calculus with standard calculus and you allow changes of variables which can mix normal numbers with Grassmann numbers, and you get some amazing stuff coming out. And also some fantastic applications in condensed matter theory as well as high energy physics. So I would love to spend more time on the Grassmann calculus, the Grassmann variables. But for this course, we only have one very specific integral that we need the whole time anyway. So it would be a bit beside the point to spend too much time on it, but yeah, you could easily get lost in this stuff. It's good fun. All right. The many variable Gaussian integral is now the objective for the rest of this lecture. And this is it. This is the main application that we want to use. Of the Grassmann calculus. The many variable Gaussian integral. What does it look like? Well, first we need the measure, the integral measure. And then we need the Gaussian itself. There's the Gaussian. Oh, we're missing out some summation signs. And this matrix B is going to be a Hermitian matrix. So this is the integral we want to evaluate today. And we're going to do it exactly the same way as we did for the normal many variable Gaussian. So how do we do it? So the first step is to make a change of variables a linear change of variables to diagonalize this matrix B. So this matrix B is not yet diagonal. Yep.
Above there, you use the convention to first integrate over theta 1, so theta 1 is on the right, and then theta n on the left. You change this convention here, please.
Ah, yeah. Okay, so there's a question. What's going on with this convention here? So the convention that I wrote up here is that we integrate over theta, then theta star. If you like. See, that's what, if you just look at this definition here. And then the question is, what's going on here? It looks like the order's wrong or different. It turns out it doesn't matter as long as you keep these theta star thetas in pairs. Because two derivatives commute with two other derivatives always. But one derivative anti-commutes with another derivative. So as long as you keep these guys in pairs, it doesn't matter if I do 1, 7, 12, 10, 2, or do the integrals in totally the other order, as long as you keep them in pairs. Because B is a Hermitian matrix, we know there is a unitary matrix U which diagonalizes this matrix B. And we're going to use this unitary matrix to define a change of variables for our Grassmann numbers. According to this, we're going to define new Grassmann numbers to be just linear combinations of the old ones like that. And then we notice that the product from theta 1 to theta n, which is what we need to do for this integral here, has a very interesting expression in terms of theta primes. Okay, so what do we get? Well, I guess I'll do it this way. I'll do the primes on the left-hand side and the thetas on the right-hand side. So this equals, well, I'll get rid of the, you know what I mean when I just write 1 K1, 2 K2, n Kn, and then we've got theta K1 all the way up to theta Kn. And there's a summation convention in place. Over these repeated k indices. Okay, I've just substituted in that into that. Now these thetas are all out of order, generally speaking. You know, there's some permutation. Is some permutation of the original numbers. And if we want to put these thetas into the correct order, then we pick up a minus sign every time we flip or transpose two of these terms. So that's what happens when we reorder these theta terms. We pick up a sign. We just pick up a minus sign, depending on did we do an even number of transpositions or swaps, or did we do an odd number? So there we go, we just get this anti-symmetric symbol here. Now remember, there's this implied summation. Yeah, I guess I'll just put the summation in that line. So it's a little exercise for you to get from here to here. It's not a particularly challenging exercise, but it's one that you should do. So what have we got here? Well, we've just reordered, I'm going to move the board up in a second. We've written down something in the brackets, which is very familiar from linear algebra. It's just the determinant of U. Yeah.
The signum has to be the signum of pi.
Ah, yeah, thank you. The psi, the question was, doesn't this have to be the sign of pi, the permutation? Yes, it does. Yeah, epsilon's the other symbol for the sign of a permutation. So pretty awesome. What we've got here is a super concrete way of going from theta 1 prime through theta n prime all the way to theta 1 through theta n. Now the reason we focus on this particular calculation is that the only term that counts for an integral is this highest order term in the many variable Taylor series. So if we go to this integral here, we can see that the only term that's going to count is the highest order term. When you expand this into Taylor series, this has got 2 to the n terms in that Taylor series. They don't all vanish, quite a few stay there. But the only term that counts, the only term that will be left over, is just the coefficient of theta 1 through theta n multiplied by theta 1 star through theta n star. So in this integral here, we can change variables at the expense of a determinant of u. Correct. So in order to evaluate this integral, we need to do the integral over the prime variables, but to do that we notice that the derivative with respect to the prime variables is related to the derivatives with respect to the original variables just via that change u. And then we remember that the integral itself is just the derivative. So then we finally get a super simple expression for this integral here. So this is and then we do the integral with respect to these variables one after the other, bringing down a factor of lambda 1 through lambda n each time. So these lambdas, of course, are just the diagonal elements of D, or if you like, they're the eigenvalues of B. And we end up with this really remarkable expression. I mean, this is interesting in so many ways. one of the most astonishing features about this, well, there's two astonishing features about this integral. Number one, we can do it. So it's not always the case that you can find a compact, nice formula for an integral even in the Grassmann world. And secondly, it looks so much like its original Gaussian counterpart, except for one key feature. Namely, that in the normal Gaussian case, you would expect to get the determinant of B inverse, or 1 on the determinant of B. Here, you just get determinant of B. So the determinant's in the numerator, not the denominator. Very strange. And it's this amazing feature that allows you to, that underlies the success of, say, certain supersymmetric methods, because this determinant factor cancels in certain Gaussians involving both normal variables and Fermi variables. I won't write that out now. I will just write out one exercise. Oh no, I will write it out. I've got a couple of minutes. So the determinant of B is a nasty nonlinear function of B. This is about as nonlinear as you can get as a function of B. And it's why a lot of calculations in quantum field theory are hard, because we've got these determinants hanging around, usually in the bottom. Before I explain this supersymmetric method in one line, I want to give you a very important exercise, namely to compute the generating function for the Gaussian integral. You should find the answer that you would expect in the classical Gaussian case. That's the answer. But you need to do it. So, and then, given this answer here, we can work out all the moments now of a Gaussian Grassmann integral. I'll just do one calculation. Star is on the other place. So you get this cool formula there, just like the classical moments, 2-second order moments. And then, as a parting comment, I'll just show you what happens when you mix normal numbers and Grassmann numbers. So if you were to carry out a double Gaussian integral, so what you do is you have a Gaussian integral over normal variables x1 through to xn, they're complex variables in this case, and Grassmann variables θ1 through θn, and you build this particular matrix M, which has the matrix A inside it twice, and you do the Gaussian integral normal one and the Grassmann integral, then you end up with the very beautiful cancellation of these A's here, of these determinants of A's here. And this allows you to do some quite magical tricks when you look at generating functions. But this is a story for another class. This is the basis for something called the supersymmetric method. We're not going to be able to reach that in this course, but it's a fun thing to notice already at this stage. Right, so in this lecture, I've introduced the Grassmann numbers and variables, functions of Grassmann variables, and defined by analogy with the real variable case a kind of calculus for these variables. And we've computed the most important result by exercise, namely the generating function for a Gaussian integral of Grassmann variables. And I think that's it for today. Thank you very much.